let's talk about some heart physiology. Now, physiology on a step is very easy, but they like to complicate it with confusing terminology and charts and graphs and stuff. So I'm gonna try and demystify it, all right? Try and define some terminology, try and really clarify some graphs and charts and make it easy for you. So we're gonna talk about heart physiology. Let's just draw out how the heart functions. We said you have a right side, right? Right atrium, right ventricle, and that pumps blood out to your lungs to get oxygen, and that eventually returns to your left side with the left atrium and the left ventricle, and that pumps blood out to your body. And via veins, it will return back to the right atrium, and the cycle will go in a circle and repeat itself, right? That is how your heart functions. We said your heart is a pump, pumps blood out, and the amount, the output that your heart pumps out is called the cardiac output. Cardiac output. Cardiac output. So this is my prop, this is my heart prop, a water bottle filled with water. That'll be the blood, right? So you pump that water, pump that blood out. And your cardiac output can change. Sometimes you need more blood, sometimes you're exercising, right? And your muscles need all that blood. Sometimes you're taking a big fat nap and you don't need that blood. So your cardiac output changes, right? What factors into cardiac output? How can it change so rapidly? Well, some things include heart rate. If I squeeze this bottle more, pump it more, quicker, you get more blood out, you get more cardiac output, right? That's intuitive. And then the other one is stroke volume, basically how much you fill it up, how much fluid's in here, how much water or how much blood is in here. If you fill it up with more, then you can pump out more. If you fill it up with less, pump out less. That is all fine and dandy, hopefully. Now, stroke volume is a little bit more complicated. There's a little bit more factors that go into it. That might be less intuitive. For example, one of the easier ones is how much you fill it with. I'll just say fill, all right? The more you fill it up with, we said, the more you pump it out. The less you fill it up with, the less you pump it out. All right, that's easy. There's another one that's less easy, that's resistance. Resistance. For example, if I put my hand over this bottle, put a lot of resistance, and I try and pump water out, will any water get out? Will any blood get out? No. So if you have a lot of resistance, then it's very difficult for that fluid to get out. Now, the last factor of stroke volume is going to be contractility. Contractility. How hard am I squeezing it? If I squeeze it really hard and I just pump all that water out, okay. If I barely squeeze it, does it really matter what all the filling and all the resistance is if I'm barely squeezing? No. So contractility is a big one, right? All right, that does it for your cardiac output. I swear I'm not going to add anything more. So we said that physiology is easy, but they like to complicate it with weird terminology. So what are some weird terminology they use for cardiac output? Instead of heart rate, they might say chronotropic. Tropic meaning change, chrono meaning pertaining to time. So changes in time, aka rate, changes in your heart rate, right? Instead of filling the bottle up with water, filling up the heart with blood, filling, they say preload. You're basically loading up the heart. Instead of saying resistance, they say afterload. After you fill up the heart with blood, what does it face? What resistance does it face? That is afterload. Afterload means resistance. Instead of contractility, they call it inotropic or inotropy. Again, tropy meaning change, ino meaning force, so changes in force, contractility. Right, you're probably rolling your eyes, but they do that. They do that. They say this person has a change in inotropy, and you're like, what's that? Contractility. The person has a change in afterload. What's that? Resistance. The person has a change in preload. They're not filling the heart up, or they're filling too much. Filling, all right? Changes in chronotropy, heart rate. All right, so very, very easy ways it can get you. If you need to take some time, put it on a flashcard, or just take some time to remember these different terms. By all means, it'll really help you moving forward if you commit these to memory. Okay, commit these to memory. So we have our. I don't think I need this prop anymore. I was actually going to drink some water, but I'll wait. We have our cardiac output. Now, how are each of these affected? Let's talk about preload first. Preload, we said, is blood filling back up the heart, right? You can increase preload. How do you think we increase preload? Well, just give more blood. So blood transfusions, just things like fluid. If I drink a ton of water and get more fluid fills the heart, more preload. So I'll write increase fluid. I'll write volume. I think that's a better term. Volume. So things like IV fluids, all that good stuff. Or if you drink a lot of water. And then something important to know is venous tone. We said that your veins hold your blood, right? Hold your blood, and it will eventually deliver it into your heart. And if you have more tone, if your veins squish that blood more, then you get more return to the heart. All right. Now what decreases preload? Well, how about decrease volume? If you're dehydrated or if you have a stab wound and you're bleeding out, if you're bleeding out, that blood's not going to your heart, right? It's going elsewhere. So dehydration, hemorrhage, and then decrease venous tone. Decrease venous tone. If your veins are not squeezing, if they're decreased tone, if they're just relaxed, then all that blood will pull down. Usually pull down to your legs. Pull down to your legs. If it pulls down to your legs, it's not going to get back to your heart. It's not going to fill your heart. You're not going to have preload. It will decrease preload. Decrease preload. All of these factors, right? And these increase preload. A drug that decreases venous tone is nitroglycerin. We get nitroglycerin that dilates our vessel. That's good for heart attacks. We'll talk about that later. But it can dilate your veins, and it dilates your vein, and the blood will pool in your veins. Won't get back to your heart. Decrease preload. So nitroglycerin is a drug that they like to test you on. Nitroglycerin. That's preload. Afterload, we said, was resistance. Resistance that your heart has to pump against. And main cause of resistance is narrowing of the vessel. Sometimes it's from like cholesterol plaques. Sometimes it's from vasoconstriction. So all right, increase afterload are due to things like vasoconstriction or narrow vessel, right? If it's very narrow, if I put my thumb over here and I try and push that water out, it's going to be very difficult. It's going to be very difficult. What decreases resistance? What decreases afterload? Well, it's going to be things that dilate the vessel. If you have a nice big vessel, you can pump blood out so easy. So easy. So things that are vasodilators. Things that are vasodilators. A drug they like to test you on is hydralazine. All right, that reduces blood pressure, reduces resistance by dilating the vessel. Makes things easy. Lowers the pressure, makes things easy. Makes things easy. Inotropy, aka contractility. We talked about one that increases inotropy. We talked about one in our arrhythmia videos. We said that sympathetic activity via catecholamines via beta-1 receptors increase contractility. If you recall how our SA node depolarizes, you have your leaky sodium channels, right? And then it can spontaneously depolarize and calcium will come in. And then finally potassium will efflux out, and then you kind of start all over again. And we said that sympathetic beta activity will increase your LF channels, make it easier to depolarize, and increase your heart rate. Shout out to your chronotropy. And it also will increase calcium, which makes it easy to further depolarize. And also, when you have increased calcium, your heart contracts more because all muscles need calcium to contract. So you have a lot of calcium, you contract more. So all right, increased inotropy due to sympathetic / beta-1. Sympathetic / beta-1. And if that increased inotropy, what do you think decreases inotropy? Decreases inotropy. Well, that'd be parasympathetic. Parasympathetic. And our beta blockers. We kind of just block that. And since we're down in decreased inotropy, some other things that can decrease inotropy are things like narcotics, because you just basically, you get zonked out. Yeah, your heart rate slows down, your respiratory rate slows down, you can actually die from that. So narcotics. How about calcium channel blockers? Calcium blockers. You block that calcium, you block that contractility. And then heart failure or diseased heart. If your heart cells are dead, they're not going to contract, okay? They're not going to contract. They're not going to have that inotropy. I like that term, inotropy. So let's just jump back into what causes increased inotropy. We talked about sympathetic beta 1. Some other things that can cause increased contractility is going to be a drug called digitalis, aka digoxin. What the heck is digoxin? Well, once you have a bunch of calcium in your cells, your body will sooner or later need to pump that calcium out, right? It can't contract forever. Contract forever. How does it do that? Well, all cells have that resting sodium, potassium, ATP, ACE pump that pumps sodium out, takes in potassium, right? And your cell will say, I can use this. And your heart cells have something called a calcium sodium pump or sodium calcium pump, doesn't really matter. And what it will do, it will take all this outside sodium and it will take it in. And by doing that, it can pump calcium out, pump calcium out. Digoxin will block this sodium, potassium, ATP, ACE pump. And when you block that, you can't pump out sodium. You can't pump out sodium. So this pump right here, this sodium calcium pump, looks for that sodium, says, where is it? I need it so I can pump out calcium. Can't find it. So calcium stays in there, never gets pumped out. Calcium stays in here, and now you have a ton of calcium, makes your contractility longer, harder, you get more inotropy. You get more inotropy. Okay, I just realized I spelled inotropy wrong the whole time. Whatever, it's too late now. That's how digitalis increases inotropy. Hopefully you understand that, okay? And then last but not least, increased preload increases inotropy. Increased filling increases inotropy, all right? See, when your heart fills with fluid, it will stretch and it will recognize that it's full of fluid and it will say to itself, I need to contract even harder. Otherwise, I'm not gonna get all this fluid out. If I contract the same, it's not gonna get all the fluid out. So I need to contract even harder. So when it fills up, when there's increased preload, it will cause it to contract even harder. Cause it to contract even harder. Let's look at it graphically. We said they like to confuse you with graphs. Let's try and unconfuse you. Here's preload. Here's cardiac output. This is a graph of our inotropy, right? Inotropy, contractility. As preload increases, cardiac output increases. That is normal. So as preload increases, cardiac output increases. That is normal. That's it. That's your graph. Not too bad, right? And we can actually plug some of these other factors in. So if you have a normal patient, you just give them things like increased sympathetic response if they're fight or flight, if they're exercising, or if you give them digoxin, then that graph will increase. So right, sympathetic, digoxin, exercise, etc. How about down here? If someone's on narcotics, if someone's getting a beta blocker, if someone has heart failure, then their curve will be decreased. Their inotropy will be decreased. Heart failure, beta blocker, calcium blocker, etc., etc. Now there's a trick question. They'll show this normal graph. They'll show this heart failure graph, and they'll say you gave that patient, the heart failure patient, something, and then now it looks like this, somewhere in between. What did you give that patient? You gave them digoxin, so heart failure plus digoxin. So you gave something that kind of boosts up their inotropy, and now you're somewhere in between. That graph, this inotropy graph, is called the Frank-Starling curve. Frank-Starling curve basically shows that as you increase preload, you increase cardiac output. Inotropy graph. Inotropy graph. One more graph, and we'll actually be all done with this video. All right. This graph is confusing to many people, and it is actually called the cardiac and vascular function curve. The reason it's confusing is because it combines different graphs, combines them together and kind of overlays them, and that makes it confusing. One of the graphs it combines is this inotropy graph, and we just kind of talked over it. You have increased inotropy here, you get a higher graph. You have decreased inotropy, With things like heart failure, things like beta blockers, or a decrease, you have a lower graph. We just talked about that. They combine this with another graph that looks at preload, aka venous return. And that kind of looks like this. Okay? And what do we say increased venous return? What do we say increased venous return? Didn't we say things like volume, increased volume? Like fluids. Didn't we say increased tone? So now this graph is increased. Well, what decreases? What decreases venous return? How about decreased volume? How about dehydration, bleeding out, all that stuff? How about decreased tone? Okay. And when they combine it together, it will look like this. With the inotropy here, inotropy, it's kind of difficult to show. Inotropy and the venous return. And they'll give you all these different situations, and they want you to show how the graph has changed. So they'll talk about someone that's taking digoxin. How will it change? Well, we said that increases inotropy, so your cardiac and inotropy graph will now look like this. Will it do anything to the venous return? Does the digoxin do anything to the venous return? No. All right, so now it looks like this. That's your new graph. It's kind of raised. Right? That's it. Or they might say this patient is taking a vasodilator, taking nitroglycerin, decreased venous tone. What does the graph look like now? Well, if you decrease venous tone, it will now look like this. Will it do anything to the inotropy? Does vasodilators do anything to the inotropy? No. All right, so sometimes you can shift just one part of the graph and not the other. That's how they trick you, all right? Shifting one part of the graph and not the other. Now you can actually shift both parts of the graph, all right? How do we do that? Well, let's just go back. I shouldn't have erased it, but let's just go back. We said that cardiac output is due to heart rate and stroke volume. And stroke volume is divided into preload, which is this graph, so we talked about that. Afterload, and contractility, which is this graph, and we talked about that. So the only thing left is afterload. Afterload resistance actually can shift both of these graphs. So let's draw it out. Here's your inotropy. Here's your venous return. If you decrease afterload, if you decrease resistance, make that vessel nice and wide, then it will be easier to pump blood through. And when you pump more blood through, then more blood will return into your veins and will return into your heart. Increase your preload, increase your venous return. So now your venous return will increase. So this actually increases both graphs, and now your new graph looks like this. And this is due to decrease resistance, total peripheral resistance. And you can imagine if you increase resistance, then you can't pump that blood out. So your cardiac output inotropy will decrease. Now it looks like this. Should use another. So now it looks like this. If you can't pump that blood out, then blood doesn't return to your heart. Venous return drops, and your new graph looks like this. So afterload resistance affects both. That is all the charts you need to know for cardiac output. Hope that clarifies some things. Hope you enjoyed the video. Thanks.